Dr. Arise Thorne, a theoretical physicist with a penchant for the profound, often found himself staring at the star-dusted canvas of the night sky, not just with wonder, but with a gnawing question that echoed the very fabric of existence: what if there are infinite versions of ourselves living out different lives? This wasn't merely a philosophical musing for Arise. It was the driving force behind his life's work, a question that had captivated the minds of scientists and philosophers alike for centuries, leading to the relentless exploration of the multiverse concept, his laboratory a chaotic symphony of whiteboards covered in complex equations, scattered research papers, and the hum of advanced computing systems was his personal portal to these grand inquiries. For Arise, the universe wasn't just the observable cosmos. It was a whisper of something far grander, a hint of realities beyond our current comprehension. The very idea of a multiverse, once relegated to the fringes of speculative fiction, was, now more than ever, demanding serious scientific consideration. The journey into the multiverse was not a solitary one. Arise was part of a global consortium of brilliant minds, each contributing their unique expertise to unraveling the universe's deepest secrets. Recent breakthroughs had ignited a new fervor in their quest. The detection of gravitational waves, those faint ripples in the fabric of spacetime, had confirmed a century-old prediction by Einstein, opening a new window into the universe's most violent and energetic events. And the meticulous mapping of the cosmic microwave background (CMB), the afterglow of the Big Bang, continued to reveal subtle anisotropies that hinted at a universe far more complex than previously imagined. These weren't just isolated discoveries. They were tantalizing clues, pieces of a cosmic puzzle that, when assembled, might reveal a tapestry of infinite realities. Arise often pondered the sheer audacity of the concept. A universe with its billions of galaxies, each teeming with countless stars stretching across billions of light years, was already an unfathomable expanse. Yet, the multiverse theory suggested this was but a single drop in an infinite ocean. It was a humbling thought, one that simultaneously diminished and elevated humanity's place in the grand scheme of things. If true, it meant our existence, our choices, our very reality, might be just one iteration among countless others. The implications were staggering, not just for physics, but for philosophy, for our understanding of consciousness, and for the very meaning of life itself. The journey had just begun, and Arise, with his insatiable curiosity, was ready to delve deeper into the heart of these cosmic enigmas. From science fiction to science fact, the idea of multiple universes or parallel dimensions had long been a fertile ground for the imagination, a staple of science fiction narratives that transported readers to worlds where every choice branched into a new reality, where alternate versions of themselves lived out different destinies. From comic books to blockbuster films, the multiverse was a thrilling concept, a playground for speculative thought. Yet, for decades, it remained firmly in the realm of fantasy, a whimsical notion with little grounding in empirical science. However, recent advancements in physics, particularly in the esoteric fields of quantum mechanics and string theory, had begun to blur the lines between science fiction and scientific inquiry. What was once a fantastical premise was now being rigorously explored by some of the brightest minds on the planet. Dr. Lena Petrova, a quantum physicist and Arise's longtime collaborator, often articulated this shift with a wry smile. "We used to joke about parallel universes over coffee. Now we're building experiments to test their implications." At the heart of this paradigm shift lay to dominant theoretical frameworks, the many worlds interpretation (MWI) of quantum mechanics and the inflationary multiverse. The MWI, first proposed by Hugh Everett III in 1957, offered a radical solution to the perplexing problem of quantum measurement. In classical physics, a particle has a definite state. In quantum mechanics, however, a particle exists in a superposition of all possible states until it is observed. The act of observation, according to the Copenhagen interpretation, causes the wave function to collapse, forcing the particle into a single, definite state. But what if the wave function never truly collapsed? Everett's audacious proposal was that every quantum measurement, every probabilistic event, didn't force a single outcome, but rather caused the universe to split into multiple, parallel branches. In one branch, the particle might be observed in stata. In another, simultaneously existing branch, it would be observed in state B. This meant that for every decision made, every coin flipped, every quantum fluctuation, an entirely new universe was born, diverging from the original. Lena found this concept both elegant and unsettling. It suggests an unimaginable proliferation of realities, she'd explained to a Reese during one of their late-night discussions, where every possible outcome of every event is realized in some universe. The inflationary multiverse, on the other hand, emerged from the theory of cosmic inflation, a widely accepted model explaining the rapid expansion of the universe immediately after the Big Bang. Inflation posits that the early universe underwent an exponential expansion, smoothing out irregularities and explaining the observed flatness and homogeneity of our cosmos. However, some models of inflation, particularly those involving eternal inflation, suggest a far grander cosmic landscape. According to the eternal inflation theory, inflation, once it starts, never truly stops everywhere. Instead, it continues indefinitely in some regions, while in others it ends, forming bubble universes like our own. These bubbles nucleate and pinch off from the inflating background, each potentially having different physical laws, constants, and dimensions. Reese found this concept particularly compelling as it offered a natural explanation for the fine-tuning of our universe's fundamental constants, which seem perfectly calibrated for the emergence of life. If there are an infinite number of bubble universes, then it's not surprising that at least one of them would have the right conditions for life to arise. Key ongoing debate within the scientific community regarding these theories was as vibrant as it was complex. While many physicists embraced the elegance and explanatory power of the MWI and inflationary models, others remained skeptical, citing the lack of direct empirical evidence and the philosophical implications. Dr. Evelyn Reed, a prominent cosmologist, known for her rigorous skepticism, often challenged the assumptions underlying these multiverse theories. While mathematically compelling, she'd argued at a recent conference, the unfalsifiability of some of these concepts pushes them to the very edge of what we consider science. How do you test for something that, by its very nature, is beyond our observable universe? Indeed, recent studies had begun to challenge some of the more expansive claims. Some researchers were exploring alternative interpretations of quantum mechanics that didn't necessitate an infinite branching of realities, while others questioned the universality of inflationary models. A paper published in early 2025 by a team at the University of Bristol, for instance, proposed a quantum innovation that, if proven, could potentially quash some interpretations of the multiverse by offering a simpler explanation for quantum phenomena without resorting to parallel worlds. 6. This intellectual friction, Reese knew, was essential to the scientific process. It was through rigorous debate and constant questioning that true understanding emerged, pushing the boundaries of human knowledge ever further. The evidence. What clues point to a multiverse? The search for evidence of a multiverse was akin to searching for echoes in a vast, silent cathedral. While direct observation remained elusive, scientists were meticulously sifting through the faint whispers and subtle anomalies in our own universe, hoping to find clues that hinted at a grander cosmic architecture. Reese and Lena, along with their international team, were at the forefront of this quest, scrutinizing every piece of data, every cosmic ripple, for a sign. One of the most compelling, albeit indirect, lines of evidence came from the very fabric of spacetime itself: gravitational waves. Predicted by Einstein's theory of general relativity over a century ago, these ripples in spacetime are generated by cataclysmic cosmic events such as the collision of black holes or neutron stars. The first direct detection of gravitational waves in 2015 by the LIGO experiment was a monumental achievement, opening a new window into the universe. But beyond confirming Einstein's genius, these waves held a deeper potential, some theoretical. Models suggested that if our universe had collided with another bubble universe in the distant past, such an event could leave a detectable signature in the form of specific gravitational wave patterns. While no such definitive patterns had been observed yet, the ongoing advancements in gravitational wave astronomy, with more sensitive detectors coming online, offered a tantalizing prospect for future discoveries. Another crucial piece of the puzzle lay in the cosmic microwave background (CMB), the faint afterglow of the Big Bang. This ancient light, emitted when the universe was only 380,000 years old, provides a snapshot of the early cosmos, revealing tiny temperature fluctuations that seeded the formation of galaxies and large-scale structures. The Planck satellite, among others, had mapped the CMB with unprecedented precision, revealing a remarkably uniform universe, but also subtle anomalies such as the cold spot, a surprisingly large, unusually cold region in the CMB. While conventional cosmology offered some explanations, some theorists proposed that such anomalies could be the bruises left by collisions with other universes in a larger multiverse. The 2025 Cosmic Microwave Background Survey, a highly anticipated international collaboration, promised to push the boundaries of our understanding even further. ERISA's team was eagerly awaiting the full data release, particularly focusing on any new insights into the CMB's polarization patterns, which could potentially reveal the imprint of primordial gravitational waves generated during the inflationary epoch. Such a discovery would not only provide strong support for inflation, but could also offer indirect evidence for the eternal inflation scenario and, by extension, the inflationary multiverse. Early indications from preliminary data released in March 2025 hinted at intriguing new details in the CMB, though definitive conclusions regarding multiverse implications were still pending. Beyond these cosmic observations, the existence of dark matter and dark energy, to mysterious components that make up approximately 95% of the universe's mass-energy content, also fueled multiverse speculation. While their nature remains unknown, some theories propose that these enigmatic substances could be manifestations of interactions with other universes, or perhaps even evidence of matter and energy leaking from parallel dimensions. While highly speculative, these ideas underscored the profound mysteries that still permeated our understanding of the cosmos, leaving ample room for radical new paradigms like the multiverse. While these observations were not conclusive proof of a multiverse, they provided compelling reasons for continued exploration. The scientific community was actively developing new techniques and refining existing ones to search for further evidence. From advanced telescopes peering into the deepest reaches of space to next-generation particle accelerators probing the fundamental nature of reality, the quest for the multiverse was driving innovation across multiple scientific disciplines. The echoes were faint, but they were there, and with each passing year, the instruments to listen to them grew more sensitive, the theories to interpret them grew more sophisticated, and the possibility of uncovering a hidden cosmic tapestry grew ever more real. The implications, if there are other universes, what does that mean for us? The existence of a multiverse, if proven, would undoubtedly be one of the most profound scientific discoveries in human history, fundamentally reshaping our understanding of reality and our place within it. For Rees, the implications extended far beyond the realm of theoretical physics, touching upon philosophy, consciousness, and the very essence of what it means to be human. The concept challenged deeply ingrained notions of free will, destiny, and the meaning of life itself. If every possible quantum outcome is realized in a separate universe, as the many worlds interpretation suggests, then every choice we make, every path we don't take, is simultaneously being lived out by another version of ourselves in a parallel reality. This raises a dizzying array of philosophical questions. Does free will truly exist if all possible choices are made somewhere? Or are we merely playing out predetermined roles in an infinite cosmic drama? Arias often debated this with his philosophical colleagues, some of whom argued that true free will could only exist if our choices genuinely narrowed the possibilities, rather than simply branching them. Others contended that the very act of choosing, even if all outcomes are realized, still represents a unique experience for each individual consciousness within its respective universe. The implications for our understanding of reality itself are equally profound. Our perceived reality, the universe we inhabit, might just be one slice of a much larger, multidimensional cake. This could mean that the fundamental constants and laws of physics that govern our universe are not unique, but rather just one set among an infinite number of possibilities, each realized in a different bubble universe. This concept, while unsettling to some, offered a powerful explanation for the apparent fine-tuning of our universe for life. If there are countless universes with varying physical laws, it becomes statistically probable that at least one would possess the precise conditions necessary for stars, planets, and ultimately life to emerge. Recent work by philosophers and physicists had begun to explore the possibility that these multiple universes might not be entirely isolated. The idea of interacting multiverses, where subtle influences or even direct communication could occur between different realities, was gaining traction in some speculative circles. Quantum entanglement, that mysterious phenomenon where two particles become linked regardless of distance, offered a tantalizing hint. If entanglement could extend across universal boundaries, it might provide a mechanism for subtle interactions, potentially leading to observable phenomena that defy conventional explanations. While still highly theoretical, the notion of a quantum bridge between universes ignited the imaginations of many, including Lena, who saw it as a potential avenue for future experimental verification. The prospect of exploring the multiverse through advanced technology was a recurring theme in Arias's more imaginative discussions. Concepts like wormholes, theoretical shortcuts through spacetime, and advanced quantum entanglement manipulation, once confined to the pages of science fiction, were now being discussed, albeit cautiously, as potential pathways to other realities. The ethical considerations of interacting with other universes were also a significant part of these discussions. What would be the consequences of introducing new technologies, diseases, or even philosophical concepts to a parallel world? The potential for unintended consequences was immense, underscoring the need for extreme caution and a deep understanding of the multiverse before any such ventures could be contemplated. The very act of observation, as quantum mechanics had taught them, could alter reality, and the thought of altering an entire universe was a responsibility that weighed heavily on the minds of those who dared to dream of interuniversal travel. The future of multiverse research quest to understand the multiverse was not a static endeavor. It was a dynamic, evolving field, constantly pushing the boundaries of human ingenuity and scientific exploration. Arias and his colleagues knew that the answers, if they existed, would not come easily. It would require sustained effort, groundbreaking technological advancements, and a willingness to challenge deeply held assumptions. The future of multiverse research promised to be as exciting as it was uncertain. One of the primary avenues for continued investigation lay in the realm of advanced observational astronomy. Next-generation telescopes, far more powerful than anything currently in operation, were being designed to peer deeper into the cosmic past to capture the faintest echoes of the early universe and to search for subtle signatures that might betray the presence of other realities. The James Webb Space Telescope JWST, already delivering breathtaking images of the early cosmos, was continuing its observations, providing invaluable data on the formation of the first stars and galaxies and offering new insights into the conditions that prevailed shortly after the Big Bang. Future missions, even more ambitious, were on the drawing board, designed to map the CMB with even greater precision and to detect the elusive primordial gravitational waves that could confirm the inflationary multiverse. 16 particle accelerators, those colossal machines that smash subatomic particles together at nearly the speed of light, also played a crucial role. By recreating the extreme conditions of the early universe, physicists hoped to uncover new particles, or forces that could provide clues about extra dimensions or the fundamental nature of spacetime, both of which were intimately linked to multiverse theories. The development of next-generation particle accelerators designed to explore quantum gravity and probe the very smallest scales of reality held the promise of unlocking secrets that could shed light on the existence and nature of other universes. 17 Beyond these grand instruments, theoretical physicists continued to refine their models, developing new mathematical frameworks that could better describe the complexities of a multi-universal reality. String theory, M-theory, and loop quantum gravity, all attempts to unify the fundamental forces of nature, offered different perspectives on the underlying structure of spacetime and the potential for additional dimensions, which could in turn provide pathways to other universes. The interplay between theoretical predictions and observational data was crucial, with each informing and refining the other in a continuous cycle of discovery. 18 The ethical and philosophical considerations would also continue to evolve alongside the scientific advancements. As the possibility of a multiverse became more concrete, humanity would be forced to confront profound questions about its uniqueness, its purpose, and its place in an infinitely vast cosmic tapestry. The very definition of life and consciousness might need to be re-evaluated in the context of countless variations across different realities. 19 Ariz often concluded his lectures with a sense of both awe and humility. The multiverse, he would say, was not just a scientific hypothesis. It was a testament to the boundless curiosity of the human mind, a reminder that the universe, in all its grandeur, held far more secrets than we could ever imagine. The journey was long, the challenges immense, but the pursuit of understanding, the relentless quest to unravel the deepest mysteries of existence, was a journey worth taking. The exciting possibilities and unanswered questions that lay ahead in the pursuit of understanding the multiverse underscore the importance of continued research and exploration, a testament to humanity's enduring desire to comprehend the cosmos and its own place within it. The many worlds interpretation, a deeper Develina Petrova, with her sharp intellect and even sharper wit, often found herself defending the many worlds interpretation MWI against its detractors. It's not as outlandish as it sounds, she'd patiently explain to skeptical colleagues. It's simply taking the mathematics of quantum mechanics seriously. The core of the MWI, as proposed by Hugh Everett III, was a direct challenge to the prevailing Copenhagen interpretation. The Copenhagen view, while incredibly successful in predicting experimental outcomes, introduced the perplexing concept of wave function collapse, the idea that a quantum system existing in a superposition of all possible states would choose one state upon observation. This act of observation, however, remained ill-defined and seemed to grant a special, almost mystical, role to the observer. Everett's genius lay in removing the observer from this privileged position. Instead of collapse, he posited that the universal wave function, which describes the state of the entire universe, evolves deterministically and linearly, never collapsing. When a quantum measurement occurs, or any interaction that leads to a branching of possibilities, the universe itself splits into parallel branches, each representing a different outcome. For instance, if a radioactive atom has a 50% chance of decaying in a given time, in one branch it decays and in another it doesn't. Both realities are equally real, equally valid, and equally populated by copies of us experiencing those different outcomes. 20. This continuous branching leads to an unimaginably vast, ever-growing quantum multiverse. Every decision, every random event, every photon absorbed or emitted creates new branches. Lena often used the analogy of a cosmic tree constantly, sprouting new limbs with every quantum interaction. Think of it, she'd say, her eyes gleaming with the sheer scale of it. Every time you make a choice, say, whether to have coffee or tea, a universe splits. In one, you're sipping espresso, in another, you're enjoying Earl Grey, and both versions of you are equally convinced their reality is the only one. This perspective offered a compelling, if mind-bending, solution to the measurement problem, eliminating the need for an arbitrary collapse mechanism. It also provided a natural explanation for quantum phenomena like entanglement, where particles remain connected even when separated by vast distances, as they are simply part of the same overarching, branching wave function. However, the MWI wasn't without its challenges. Critics often pointed to the apparent lack of probability in a system where all outcomes are realized. If every possibility occurs, how can we talk about the probability of a specific outcome? Proponents of MWI, like Lena, argued that probability emerges naturally from the structure of the branching, where some branches are thicker or more frequent than others, reflecting the statistical weights of the quantum states. Another common criticism revolved around the sheer extravagance of an infinite number of universes. Is such a vast and untestable hypothesis truly scientific? Lena countered that the MWI was the most parsimonious interpretation, requiring fewer ad hoc assumptions than other interpretations that introduced nonlinear or non-unitary processes to explain collapse. The debate continued, a vibrant intellectual battleground where the very nature of reality was at stake. Asterisk the inflationary multiverse, bubbles in the cosmic foam. While the MWI delved into the quantum realm, the inflationary multiverse theory painted a picture of cosmic grandeur on the largest scales. Maurice Thorne, with his cosmological expertise, found this model particularly elegant in its ability to address several lingering puzzles of the Big Bang theory. The standard Big Bang model, while successful, struggled to explain the observed flatness, homogeneity, and isotropy of our universe, as well as the absence of magnetic monopoles. Cosmic inflation, proposed by Alan Guth in the early 1980s, offered a brilliant solution, an extremely rapid, exponential expansion of the universe in its earliest moments, smoothing out any initial irregularities, but the story didn't end there. Many inflationary models, especially those involving a scalar field that drives inflation, naturally lead to a phenomenon called eternal inflation. Once inflation begins, it doesn't necessarily stop everywhere simultaneously. Instead, it continues indefinitely in some regions, while in others it ends, forming bubble universes that nucleate and pinch off from the inflating background. Imagine a vast, ever-expanding ocean of inflating space, constantly bubbling with new universes forming within it. Our own universe, in this scenario, is just one such bubble, a pocket where inflation has ended, allowing matter and energy to form and evolve. What made the inflationary multiverse so compelling to Maurice was its potential to explain the apparent fine-tuning of our universe's fundamental constants. The laws of physics, the strength of fundamental forces, the masses of particles, all seem exquisitely balanced to allow for the emergence of stars, galaxies, and ultimately life. If these constants were even slightly different, our universe would be a barren, lifeless void. This fine-tuning problem has often been cited as evidence for a cosmic designer. However, the inflationary multiverse offers a scientific alternative. If there are an infinite number of bubble universes, each with potentially different physical laws and constants, then it's not surprising that at least one of them would have the precise conditions necessary for life to arise. We simply find ourselves in one of the habitable bubbles because, well, we couldn't exist anywhere else. This is known as the anthropic principle. 24 Maurice often used the analogy of a cosmic lottery. If you buy only one ticket, he'd explain, winning the jackpot seems incredibly improbable. But if you buy an infinite number of tickets, it becomes a certainty that someone, somewhere, will win. We are simply the winners of the cosmic lottery, residing in a universe where the numbers happen to align for life. This perspective shifted the question from why is our universe so perfectly suited for us, to given an infinite number of universes, what kind of universe would we expect to find ourselves in? 25. However, the inflationary multiverse also faced its share of criticisms. One major challenge was the measure problem, how to assign probabilities to different outcomes within an infinite multiverse. If there are infinitely many universes, how do we compare their relative likelihoods? This remains an active area of research. Another concern was the lack of direct observational evidence for other bubble universes. While the theory was mathematically robust and elegantly solved several cosmological puzzles, its predictions were often beyond our current observational capabilities. Despite these challenges, the inflationary multiverse remained a leading contender in the scientific quest to understand the ultimate nature of reality, offering a grand and inspiring vision of a cosmos far vaster and more diverse than previously imagined. 26 Gravitational waves, ripples from other realities. The detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory LIGO was a triumph of modern physics, confirming a key prediction of Einstein's general theory of relativity a century after its formulation. These ripples in the fabric of spacetime, generated by the most cataclysmic events in the cosmos, colliding black holes, merging neutron stars, and supernovae, offered a completely new way to observe the universe, a gravitational window. Alongside the electromagnetic one, for Reese and Lena, however, these waves held an even more profound potential. They might be the faint echoes of other universes. 7. The theoretical framework for detecting such echoes was complex, but the premise was tantalizing. If our universe is indeed a bubble in a larger multiverse, it's conceivable that it could have collided with other bubbles in the distant past. Such cosmic collisions, if they occurred, would generate unique gravitational wave signatures, distinct from those produced by astrophysical events within our own universe. These signatures might manifest as specific patterns of polarization or anisotropies in the gravitational wave background, a faint hum of gravitational waves permeating all of space. 8. Lena, ever the pragmatist, emphasized the immense challenge. Imagine trying to hear a whisper from across a continent while standing next to a roaring waterfall, she'd explained. That's roughly the scale of the challenge in detecting these interuniversal gravitational waves amidst the cacophony of astrophysical sources. Yet, the advancements in gravitational wave astronomy were rapid. With the advent of more sensitive detectors like the advanced LIGO and Virgo and the planned next-generation observatories such as the Einstein Telescope and Cosmic Explorer, the ability to discern these subtle signals was steadily improving. The hope was that future observations might reveal anomalies in the gravitational wave background that could not be explained by conventional astrophysics, forcing scientists to consider a multiverse origin. 27. The cosmic microwave background, a window to the multiverse's edge. Perhaps the most compelling, and certainly the most studied, cosmic relic is the cosmic microwave background (CMB). This ancient light, a faint glow permeating the entire sky, is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. The CMB is remarkably uniform, but embedded within it are tiny temperature fluctuations, anisotropies, that represent the seeds from which all the large-scale structures in the universe, from galaxies to galaxy clusters, eventually grew. 9. For years, cosmologists have meticulously mapped these fluctuations, first with COBE, then WMAP, and most recently with the Planck satellite, achieving unprecedented precision. While the CMB largely confirms the standard cosmological model, some intriguing anomalies persist. One such anomaly is the cold spot, a surprisingly large and unusually cold region in the CMB that deviates significantly from the statistical expectations of a random distribution. While various explanations have been proposed, including statistical flukes or unknown foreground effects, some theorists have speculated that such features could be the bruises or imprints left by collisions with other bubble universes. In the early Cosmos, 28 Aris was particularly excited about the prospects of the 2025 Cosmic Microwave Background Survey. This ambitious international collaboration, utilizing next-generation ground-based telescopes and potentially new satellite missions, aimed to map the CMB with even greater angular resolution and sensitivity, particularly focusing on its polarization patterns. The polarization of the CMB, specifically the B modes, is considered a potential smoking gun for primordial gravitational waves generated during the inflationary epoch. If these primordial gravitational waves are detected with specific characteristics, it would not only provide strong evidence for cosmic inflation but could also offer indirect support for the eternal inflation scenario and, by extension, the inflationary multiverse. Preliminary data from the 2025 survey released in early spring had already generated considerable buzz, while not yet conclusive. The data hinted at subtle deviations from the standard model's predictions in certain polarization patterns. It's like finding a faint, unusual ripple in a pond that you thought was perfectly still, Aris had told Lena, his voice barely containing his excitement. It doesn't prove there's a fish, but it certainly makes you wonder what's beneath the surface. The full analysis of the 2025 CMB data, expected by the end of the year, was eagerly awaited by the entire cosmological community, as it held the potential to either solidify or challenge some of the most fundamental assumptions about our universe and its potential multi-universal origins. 29. Dark matter, dark energy, and other cosmic enigmas beyond the direct observations of gravitational waves and the CMB. The very composition of our universe presents profound mysteries that, for some, hint at the possibility of a multiverse. Dark matter and dark energy, to enigmatic components, collectively constitute approximately 95% of the universe's total mass energy content. We know they exist because of their gravitational effects. Dark matter holds galaxies together, and dark energy is responsible for the accelerating expansion of the universe, but their true nature remains elusive. 11. For some theoretical physicists, these cosmic enigmas are not merely gaps in our understanding but potential windows into a larger reality. Could dark matter be composed of particles that only interact gravitationally with our universe but are otherwise part of a parallel dimension? Could dark energy be a manifestation of the vacuum energy of a larger multiverse, or perhaps even the subtle influence of other universes on our own? These are highly speculative ideas, but they underscore the profound limitations of our current understanding of the cosmos. If our universe is just one bubble in a vast multiverse, then it's conceivable that some of its most perplexing features could be explained by interactions or influences from outside our observable reality. 30. Moreover, the apparent fine-tuning of the fundamental constants of physics, often referred to as the anthropic principle, continues to be a powerful, albeit controversial, argument for the multiverse. The precise values of constants like the strength of the electromagnetic force, the mass of the electron, or the cosmological constant seem almost miraculously calibrated to allow for the existence of stars, planets, and life. If these values were even slightly different, the universe would be a sterile, lifeless place. While some see this as evidence of a divine creator, multiverse proponents argue that it's a natural consequence of an infinite ensemble of universes, each with different physical laws. We simply find ourselves in the universe that allows for our existence. 13. While these lines of evidence are indirect and often speculative, they provide compelling reasons for continued exploration. The scientific method thrives on challenging assumptions and seeking explanations for observed phenomena. The multiverse, while still a hypothesis, offers a framework within which some of the most profound mysteries of our universe might find their answers. The quest is ongoing, driven by the relentless curiosity of scientists like Reese and Lena, who believe that the universe, in all its complexity, holds secrets far grander than we can currently imagine. The faint whispers of other realities, once dismissed as mere fantasy, are now being meticulously sought in the cosmic data, pushing the boundaries of human knowledge to its very limits.